Welcome to topic 8.6, Gauss's law, daily video number 4. In this video, we will apply Gauss's law to spherically symmetric examples. My name is Easton Landry, and I teach at the Kinder High School for the Performing and Visual Arts in Houston, Texas. So let's do a brief review of a couple of these concepts we've discussed about Gauss's law. So for Gauss's law, it relates electric flux through the charge that's enclosed by that surface. So we have this charge enclosed, and that's our closed surface integral of our surface. Our Gaussian surface is that three-dimensional closed surface like we said before. The third one we're going to expand on the next slide a little bit more, but let's think about it briefly. It says the total electric flux through a Gaussian surface is independent of the size of the Gaussian surface as long as the total amount of charge enclosed remains the same, or remains constant, I should say. This might seem weird, but it's basically saying this left side has to always equal, not necessarily the E field, but this whole left side has to be constant if our charge is also constant. And we have our last kind of point to think about is that Gaussian surfaces are constructed such that the electric field generated by the enclosed charge is either perpendicular or parallel, resulting in simplified surface integrals. This is what we mean by the left-hand side being simplified, because if we pick easy shapes like the Gaussian plane or the Gaussian pillbox, our Gaussian cylinders, and our Gaussian spheres, it makes it much simpler, making the right side be the side that is the tricky side. But let's just briefly expand on 3 and what it's talking about. So looking at 3, if I have my surface there, inside of an insulator, my charge, if it had a variable charge density, my charge would change as a function of radius. So flux would also change. But once I'm outside the surface of the charged object, there's no additional charge I'm accumulating as I move outwards. So my flux is constant. Key thing, my E field can change as you see the leaf fields getting further apart. So it's going to get less and less and less. But the overall flux, as I make my Gaussian surface bigger or smaller, as long as I'm outside of the surface, would be the exact same. So that's kind of a key thing to note, is that the E field versus flux. Okay, so then let's look at an example with our spherical symmetry. Well, we have an insulating sphere. That's this time we have a radial charge density that's alpha over R is what we're providing you. I want an electric field less than R and then greater than R. I know this thing looks like it's a disk, but just know for all these parts of the video, this is just going to be a sphere. So once again, we're going to tackle the easy side. Hooray! This easy side, which is all done, is just going to be a Gaussian surface, which is our 4 pi r squared, a surface area of a sphere that's inside of our sphere. This charge enclosed, however, is that tricky side, and that's what we're going to hop to on this next slide. So as we explore the tricky side, we know that charge enclosed has to be our volumetric charge density times that infinitesimally differential volume element. So what does it look like? Well, we need to break this thing down into what dV is. We know what rho r is going to be, but we don't know what dV is. Well, dV is the area that we end up selecting times some thickness dr. Well, here is our Gaussian surface area, and it has this, there's our area, and it has this tiny little thickness dr. Essentially, it's a spherical shell that's very, 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 very thin, such that it is going to give us a volume. I always use this example, but people think it's weird. Imagine a spherical pizza, right? If you have a pizza dough and you stretch it out so it's hollow on the inside, you're going to get this crust. You still have volume there. You have all your dough, but the thinner and thinner you make your dough, the bigger that area is going to end up being. Anyways, helps me out. But spherical pizza, that's what I'm going for with this shell. Well, if we plug this term into our equation and we cancel out our terms and we integrate on this next slide, we are going to find that when we set our bounds from 0 to r, that sure enough, power rule, we're going to get our r squared over 2, and we're going to get our total charge enclosed. Now, we can simplify this, but we're not going to. You'll see why on this next slide. If you don't know, if you wouldn't know to do it, you're absolutely welcome to simplify. So here we go, kind of clicking right along. We solved for the hard part using calculus. So when we put it all together, I have my left side being my 4 pi r squared, my right side with my 4 pi alpha over r squared over my 2 epsilon naught. And that's why I left it there to get my 4 and my r squareds out. So sure enough, for my electric field less than r, it's going to be my alpha over 2 epsilon naught. Crazy. It just so works out that my electric field is going to be constant inside of the sphere. That's not always what's going to happen, but it did because of our function of our volumetric charge density. So that's kind of cool. Well, let's look about what's happening on outside. Outside, once again, we tackle the easy side first, where we know our Gaussian surface is going to be a sphere. That's just going to have a surface area of 4 pi r squared. And then we have our right side, which as much as we might think it's a bunch more work, it's not, because we've already done it. Now I'm just changing my bounds. Instead of integrating to r, little r, I'm going to integrate to big R, which is the bounds of my cylinder. When we do that, we're going to get this equation, as you can look back to the calculus from before. And we put this all together, we're going to notice that this time my 4 pi's cancel, and instead I'm left with this term that has an r squared on the bottom, little r. Remember, little r is our variable that's changing as we go bigger and bigger. Big R is the actual radius of the sphere itself going through. So one thing that's kind of helpful when you think through, this one is a sphere, right? So it's this r squared, not r. But one thing that I think is always helpful is to plot and graph electric fields when you solve for equations like this, because I think it helps visualize what's going down. Well, when we are inside of the surface, because it's a constant, we know that this entire region between r is just going to be zero, not zero, but a constant, this alpha over 2 epsilon naught. With this other part, we know it's going to be a 1 over r squared variable. What I like to do is plug in right at the bounds, right at r. This is going to make it be that value to start. And if I double my radius, doubling radius on the bottom means it has to have 4 times less, or 1/4 the amount, because it's r squared. So 2 squared gives me 4. So 1/4 that previous value. And I'm going to plot that dot. Well, sure enough, that's going to make my graph look something like that. Kind of asymptotically, but not ever actually reaching 0, but kind of decaying in that manner. This is a good way to kind of plot things using functional dependence. So let's do another practice. For this one, we have a conducting sphere with an insulating shell. So here's our conducting sphere, and here's our insulating shell. This insulating shell has a uniform charge density of rho. The inner radius ends up being 2a for that surface, and the outer radius being 3a. And as shown, it equates to a total charge. This whole thing has a total charge of negative 2q. I want to sketch the electric field as a function of radius for the entire shape. So once again, this is a sphere, not a disk. So what do we know? Well, let's start out for inside for our little Gaussian surface, which once again is a sphere. It's 0 inside of there because this is a conductor. Well, in this next region, you might be like, oh, I have to do like the whole integral thing for this one. But remember, because this is a conductor and all the charges enclosed, we can treat this as a point charge. That means we can use Coulomb's law. So all of this, the only charge we have enclosed is q, so kq over r squared, or 1 over 4 pi epsilon naught, q over r squared. We didn't even need to use Gauss's law to solve this. We could just use Coulomb's law. The same thing is true for the outside. When you look at all the charge enclosed, it's just going to be a total of our positive q and negative 2q. So the total charge enclosed is negative q. And so sure enough, we end up getting the exact same thing. So we get these equations. I'm saying this because if this is on the exam, we want to maximize our time. There's certain regions that are easier to solve for and certain ones that are harder. And certainly this region here inside the insulator is going to be the most difficult one to plot. So let's save that one for later. So looking at our graph here, we know that the first part, the E field has to be 0 because we're in the conductor. We know it's our value. If we plug in 4a when we first leave it, that's our maximum that's going to occur. And it's going to decay down to this value at 2a. Giving us our 1 over 4 squared, thinking that whole functional dependence like we did previously. This whole middle region, we're going to kind of skip for now, but then I know that outside of it, I'm going to once again plug in my bounds to be 3a is where I locate on the outside, and that one's going to decay at 1 over r squared facing that direction. So for this middle region, which is all we have left, we got most of the parts of this graph completed, and that's ideal. But what about that one, if you're really curious? Well, there's a conceptual solution. One conceptual solution is to recognize we're trying to find the point where charge enclosed would be 0. That's going to happen, if we look at our midline, has to be greater than 2.5a. Why? There's more charge located on an outer edge than there would be on the inner edge. It says it was uniform charge density, remember? So that means this has to be shifted outwards just a little bit. So because we know that has to be the case, we know that the dot has to be somewhere in here. We can kind of connect it like that and say, yeah, sure, good enough. But what if you don't like that and you'd rather actually solve for it? Well, if we're going to solve for that in a second, but if ever a region seems funky, the key thing to remember is you should just estimate relevant points, see if it's increasing, decreasing, or constant, and then estimate the concavity. What I mean by that is it can be straight, curving up, or curving down. Oftentimes, this is all the rubric's looking for, and if you miss that one point, you might miss that one point, but you're going to save so much time in actually solving it. To prove it to you, let's see what it would take to solve this one on the next 3 slides. This is how you're going to solve it. I'm not going to spend the time talking through it. I'm going to have each of these slides kind of appear. So here's what we're going to start with. We're going to hop to this next slide to kind of find what we eventually get in the end. And just to prove that we're right, we're going to check our bounds at 2a and 3a to get these final equations. And it does work out just for funsies. So what should we take away from this video? The main thing is whenever you're using Gauss's law, determine if it's a conductor or an insulator, draw those Gaussian surfaces, those big 3, solve for the surface integral using your little r, set up your charge density for your enclosed charge, and then integrate with proper bounds. And then finally, sub in to solve for Gauss's law and solve for that E field. And with that, Thank you for all your efforts here on Gauss's law, and I look forward to seeing you in future videos.